In this videocast, we'll look at the quantitative aspects of electrolysis. Electrolysis is where we use an outside source of electricity or of electrons to drive electrons into a substance, whether it be a molten salt or a solution. If we have a battery or a source of some type of potential difference or some source of current, we can take the electrons from it, drive it into a solution, take the electrons, and this area where we're driving the electrons into is called the cathode, because the cathode is where reduction takes place. And remember, reduction is the gain of electrons. Conversely, we also need an anode, and the anode is where oxidation will take place. To be able to look at the quantitative aspects of this electrolysis, we need to have some type of link between how much electrons or how many electrons we're putting into this substance and the amount of charge that we've actually added to it. This link is actually really similar and actually can be illustrated as just another portion of the mole wheel, or another portion of another aspect, or I guess you could say leg of the wheel, where you can convert from charge amount to amount of substance or moles. And if you remember back, we've had a number of different ways to convert from mass to moles using the periodic table, from volume of a gas at standard temperature and pressure to moles, where we've used 22.4 liters in a mole, and from particles to mole, where we've used 6.02 times 10 to the 23rd things to convert between particles or number of atoms, molecules, ions, even electrons, and moles. In this portion of the mole wheel, though, we're going to look at a way to convert and link amount of charge and moles of electrons. Well, first of all, charge is measured in a unit called coulombs. And so we're going to look at a way to convert between coulombs of charge and moles. And it turns out that there are 96,500 coulombs in a mole of electrons. And so if we're going to convert from moles of electrons to coulombs of charge, we can multiply by 96,500 coulombs per 1 mole of electrons that are transferred. If we're going to convert from coulombs of charge to moles, we can say that for every 1 mole of electrons, there are 96,500 coulombs of charge. And so this link right here between moles and coulombs of charge becomes our method of finding out how much charge is transferred or how much of a substance is created or produced or used up in an electrochemical reaction, an electrolysis reaction. The second thing we need to know, besides this link between coulombs and moles, is a definition of how much charge there is occurring per second or per amount of time. This is measured in something called amps, and an amp is equal to a coulomb per second. And remember, you can take something like this and put it into a triangle where you can say an amp is equal to a coulomb per second, and then depending on which two of the three things you know, you can cover up and find the third. Ampere is equal to coulomb per second. Coulombs would be equal to amperes times second. And of course, if you wanted to find time in seconds, it'd be a coulomb divided by an amp. So if you remember these two relationships, the coulomb, ampere, and seconds, and also the 96,500 coulombs per mole of electrons, relationship between amount of charge and moles, you should be able to do all of these quantitative, mathematical, in other words, electrolysis sample problems. This, by the way, this 96,500, just like we gave this the name Avogadro's number, this is called Faraday's constant, or Faraday's number. Let's proceed to a couple of sample problems right now. You'll find these in your packet later on. This happens to be about page 28 or 29 or 30 or so in the electrolysis sample problems. The first problem says calculate the number of grams of aluminum produced in 1 hour by the electrolysis of molten AlCl3 if the current is 10 amperes. Well, the first step in any one of these types of problems is to make sure that you write the balanced chemical equation, and you're going to need the balanced half reactions to make this work. Since this is a molten salt, we assume that we have some aluminum plus 3 ions in there, because it's molten, those ions are in there, and we also have some chloride ions in there as well. And you notice that since it's AlCl3, we'd actually have 3 of those ions for every one of the Al plus 3s. So when we drive the current in here, we're going to take aluminum and we're going to give it some electrons, and we're going to form aluminum solid, or aluminum with a 0 charge right up here. The chlorine, on the other hand, that's going to lose electrons, and we're going to end up with some just plain chlorine here on the right-hand side of the equation. And if you remember balancing half reactions, first you balance everything except hydrogen and oxygen, and so we'll have to balance this by putting a 3. Let's see, we've got 3 chloride ions here, so we're going to have to figure out a way to get this balanced over here. And actually, probably the best way to do this is to just go ahead and double this and say that we've got 6 of these, and then we end up with 3 of these over here. And then the chlorides, let's see, we're going to end up having 6 electrons over here to balance out the 6 negatives over here. The aluminums, on the other hand, we're going to have to add 3 electrons to, but I wrote it kind of lightly because if you notice the electrons don't match each other, and so I'll have to end up doubling this, which means I'll have 6 electrons here, and 2 of these and 2 of these, and I could combine the reaction together and then have an overall balanced redox reaction. The important part here is to notice, though, that 6 electrons are transferred. 6 electrons are transferred. Okay, so that's the first step, is to write your balanced half reactions. Once you've seen that, you can know the number of electrons that are transferred. And then the second step, once we've written the balanced half reactions, is to use our relationship of amperes, or our amount of current per second, is equal to coulombs per second. And if you look in here, we're given that we have 10 amperes of current driven in there, so we know amps. And we're also told an amount of time, happens to be in hours. But by doing that, we can find the amount of coulombs of charge. And if we can find the coulombs of charge, then we can use our relationship in the mole wheel that we just learned. We can go from coulombs of charge to moles of electrons transferred. And of course, our equation gives us a relationship between electrons transferred and the amount of aluminum that will be produced. And that's ultimately our goal, is to find out the grams of aluminum produced. But if we find moles of that, we can convert it to grams. So from this equation right here, if we want to find coulombs, cover up the C. It equals amperes times seconds. We're told that we have 10 amps, or I'll write it as coulombs per second. And there's 1 hour's worth of time, and in seconds, that's 3,600 seconds. And if you multiply these two together, you end up with just your coulombs of charge. Continuing on now, we can use our relationship in the mole wheel, where we can convert from coulombs of charge to moles by using Faraday's constant, 96,500. So if I have coulombs right now and I want to convert to moles, I'll put 96,500 coulombs in a position where it's going to cancel, and moles of electrons that are transferred on the top. This will give me my moles of electrons that need to be transferred to produce my aluminum. Now if I look at the balanced half reaction, notice that for every 6 electrons that are transferred, 2 aluminums are formed. And so I can write a relationship saying that for every 6 moles of electrons that are transferred, 2 solid aluminum atoms or 2 solid moles of aluminum are formed. I'll put Al with a little 0 up here since we know it's aluminum solid that was formed. Now, since we know the number of moles of aluminum, we can convert that to grams. And using the periodic table, there are 27 grams in 1 mole. And if I multiply all those all together, I should end up with something around 3.36 grams of aluminum. This may be off by just a little bit from your calculations. Your book uses a little more exact value of 96,500 coulombs. I think it's 96,482 or something like that. I could be off on that a little bit. So looking back at the overview of the steps once again, first of all, what we did was balance the half reactions. Second of all, we converted to charge. Once we got the charge, we used the link between charge and moles of electrons, 96,500 coulombs in a mole. And then we used the balanced half reaction to find out how many moles of the substance that's being produced is created, and then we convert it to grams. Let's look at a second sample problem. This one's very similar, but it's just kind of like the backwards of the question. This one says, how many seconds would be required, seconds, now we're looking for time, to produce 48.6 grams of magnesium from MgCl if the current is 100 amps. Now I'm going to assume this is molten. That means it's heated up so it actually was melted. And I think if you look at the sample problem in your textbook, which is around page 885, this is in Brown-LeMay, and this is edition 10. 10th edition, so the page number might be different if you have a different edition. We're going to assume that it's a molten substance, so we've got in there some magnesium ions, and we also have in there some chloride ion, 2 chloride ions as well. So we start the same way that we did with the last problem, where you'd write the balanced half reactions first, so you know the number of electrons transferred. Once you know that, then you can take our amount that we have, our grams, convert it to moles, use the balanced chemical equation to find out how many moles of electrons are transferred, and then use our link between moles of the substance and coulombs of charge to find out how many coulombs have transferred. And then lastly, since we can find time by relating current, coulombs, and time, if you cover up for seconds, it equals coulombs per amp, and we'll use that right at the end. So our balanced half reactions will be magnesium going to Mg solid, and then our chloride ion here will go to Cl2, and in this case we're gaining 2 electrons, and in this case we're losing 2 electrons. Those are our balanced half reactions. Nextly, to take it to our amount that we have, 48.6 grams, and let's convert that to moles. In 1 mole of magnesium, we have 24 grams approximately. Get that from the periodic table. Secondly, for every 1 mole of magnesium that's formed, I'll call it Mg0 up here because it's solid magnesium, there are 2 electrons of moles that are transferred. So I look at my balanced half reaction to find that out, to find out how many moles of electrons are transferred. Then I use my link. My link tells me that there are 96,500 coulombs of charge for every 1 mole of electrons that's transferred. So I'm going from moles of electrons to coulombs of charge. Remember, we get that from the mole wheel right here, where I go from moles of electrons that I have to coulombs of charge right here by using this link right here. Once I figure out how much charge I have, then I can use my triangle where amperes are equal to coulombs per seconds. And since they're asking for seconds, I can solve for seconds. So if I punch these into my calculator, I end up with about 390,825 coulombs. And then I can take this and solve it for seconds. Seconds are equal to coulombs per amperes. And my coulombs are 390,825. And my amperes up here are 100 amps. That's what I'm told in the question. There are 100 amperes of current. And if I want to make my units right, I guess I could use coulomb per second down here. Notice the coulombs cancel with the coulombs, and I have 1 over 1 over seconds, which actually ends up as seconds. And so I end up with 3,908.25 seconds.